Here we are given the equation of the line in the Cartesian form. Let me write it down here. So this is x plus 1 over 4 is equal to 2 minus y over 3, and this is z. But the equation of a line in a Cartesian form is not exactly the most useful for us, so let's try to convert it into the vectors form. So the equation of the line in the vectors form, equating this to, let's say, lambda and making x, y, z the subject, I will be getting the equation of this line in the vector form as r is equal to minus 1, 2, 0 plus lambda of 4, negative 3, 1. So what the question says is that the plane P2 is going to be containing this line. So let me try to do a sketch for the situation that is happening now. So for the plane P2, the equation is given to us as r dot alpha 3 beta. This is equal to 7. And this line L1 is lying on P2. So for this line, we know this point is going to be on the line L1. So the point minus 1, 2, 0 lies on L1, which also means that this point lies on P2. So let's make use of this information. Since this point lies on P2, it should satisfy the equation of P2. So making use of the position vector of this point to replace r over here, we have a minus 1, 2, 0 dot alpha 3 beta. This is equal to 7. Nice, because beta will disappear when I try to evaluate this. We are going to be getting a minus alpha plus 6 is equal to 7. This tells me that alpha here is negative 1. There's a second piece of information that I can make use of, which is the fact that this line L1 is parallel to 4, negative 3, 1. So let me try to draw it, let's say, as this. So this is 4, negative 3, 1. And for P2, the normal is alpha 3 beta. So the normal to the plane P2 will always be perpendicular to any line that is on the plane, including L1, which means that this normal will be perpendicular to this. Okay, so this is alpha 3 beta, which is perpendicular to this. So this dot this is going to be equal to 0. Okay, so let's do this. So from here, it will be a 4, negative 3, 1 dot alpha 3 beta. This is going to be equal to 0 because they are perpendicular to each other. So we have a 4 alpha. Alpha is actually minus 1. So this, then minus 9 plus beta. This is equal to 0. This will help us to solve for beta. Beta is going to be equal to 13. This is part A. Let's move on. Let's take a look at part B. For part B, we are looking at the line of intersection between P1 and P2. So we need to solve them as a pair of simultaneous equations. So for the equation of P1 that is given, we are given for as a vectors form, okay, for the plane P1. We need it to be in the Cartesian form in order for us to solve for the simultaneous equation. So let's first try to find the normal to P1. We know that from the vectors equation, P1 is parallel to 0, 1, 1 and 3, minus 1, 2. So I'm going to cross them, taking the two vectors that are parallel to the plane. Crossing them will give us a vector that is perpendicular to the plane. So I'm going to take 0, 1, 1 cross 3, minus 1, 2. And this will be giving me a 3, 3, minus 3. So this is going to be a vector that is perpendicular to P1. And I'm going to use a simpler form since the direction is the one that I need. So I'm going to use 1, 1, minus 1 as the normal to the plane P1. So from here, we can form the equation of P1. This will be r dot 1, 1, minus 1 is equal to the position vector of a point that is on P1. Okay, from the equation that is given, can you see the position vector of a point that is on P1? 0, 0, 0, right? Because it is not present, nothing is present here in front of these two vectors. So we can assume that 0, 0, 0 should be lying on the plane P1. Okay, so if it were to be 0, 0, 0 dot this, it is going to be 0. Okay, so this is the equation of P1 in the dot product form, which we should be getting this in the Cartesian form. So replacing r by x, y, z, So x, y, z dot this will be x plus y minus z is equal to 0. This is equation number 1. For equation number 2, it is going to be from P2. And according to what the question says, although we have already solved for alpha and beta, but now we are given a new alpha and beta. So alpha is negative 3 and beta is 2. So we have this is equal to 7. And replacing r by x, y, z, dotting this, it is going to be equal to negative 3x plus 3y plus 2z. This is equal to 7. This is going to give us our second equation, and pressing these two equations into our graphing calculator should give us the equation of the line, and the equation of that line will be r is equal to negative 7 over 6. 7 over 6, 0 plus, I'm going to go for mu, okay, since we have used lambda here. So mu of here, it will be 5, 1, 6. This is for part B. Let's take a look at the last part, part C. For part C, we have plane P3, which is given to us in the Cartesian form, but we can definitely rewrite P3 in the dot product form. It is pretty easy. It is going to be r dot 1, oh, not 1, 0. Okay, I've almost missed this because there's no x. Okay, so x is going to be, the coefficient of x is going to be 0. So 0, then the coefficient of y is 1, and then 3 is going to be equal to minus 4. Okay, so this is the equation of the plane P3 in the dot product form. The question says that P3 is parallel to L1. We want to find the distance between L1 and P3. So the diagram can look something that is like this. Okay, if I were to look at it from the side, so L1 is here, for example, let's say P3 is here. So the equation of P3 is this. As for L1, we have the equation here. And in order for us to find the distance between L1 and P3, I am going to make use of a point that is on L1. And this is a good point to use. I'm going to let lambda be equal to 0. So it is going to be minus 1 to 0. So let's try to find the distance between this point and P3, because this distance will also be the distance between the line L1 and the plane P3. And I'm going to make use of a process that we have been using on the Achevas TV, which is to create a plane that is going to be parallel to P3 and passing through minus 1 to 0, okay, to find this distance. So for that plane, I'm going to go for pi, okay, to name that plane that passes through minus 1 to 0. And since this plane that passes through this is going to be parallel to P3, so I'm going to use the same normal vector, 0, 1, 3. It's going to be equal to, since this is going to be the point that is on this plane pi, so it will be minus 1 to 0 dot 0, 1, 3, which is going to be equal to 2. So based on this, and this, I can find the distance between these two planes, which will also be the distance that is between this point and P3, which will also give us the distance between L1 and P3. So the distance between L1 and P3 will be the distance between these two planes, and that will be making use of the process that is in our, that is on the Achevas TV. It is going to be 2 over the modulus of 0, 1, 3 minus 4 over modulus of 0, 1, 3. Okay, so 2 plus 4, this is going to be equal to 6, divided by, this is going to be square root of, okay, let me just write it down, square root of 0 square plus 1 square plus 3 square. So our answer here is 6 over square root of 10.